welcome to ITC Battlestar Galactica. I think this is episode number 4, is that right? Maybe? So today we are very fortunate to have 2 of our own, Joel Leja and Matt Ashby. Joel's an NSF postdoctoral fellow here, and Matt Ashby is an astrophysicist. I maintain the vaguest title you can possibly have at this institute. And today they're going to talk to us about how we interpret the infrared SEDs of galaxies. And this is obviously a key uncertainty in our understanding of galaxy formation and evolution, how we go from the light we observe to actual physical properties of galaxies. And in particular, in the last couple of years, the infrared has been quite contentious in terms of how we interpret it. So we're very fortunate to have these experts here. Take it away, guys.
Thank you, Erica. So we're going to do something a little different today. We decided to blend our slides into one presentation, and we're going to tag team it in a friendly way. Joel's going to begin by introducing SEDs, even though we know that for this audience, this is an expert audience. I'm supposedly going to be take the IR observer role here. I took my mandate in this fight, this debate, to be one of trying to poke some holes or find some weaknesses in our current knowledge of spectral and our understanding of spectral energy distributions. So that's kind of where I'm going to focus, since this is such an expert group already. And Joel is obviously one of the experts, so that's kind of where we're taking it. So with that, why don't you begin, Joel?
Thank you. All right, I'll take over now. Yeah, so like Matt said, I'll be sort of introducing the basics and talking about the canonical way we interpret these things, and then Matt will get into some more of the details and some more of the caveats. And hopefully having 2 different views on sort of similar topics will be illustrative for everyone here. So just to quickly get to the basics, SED fitting is the process of taking these very beautiful images of galaxies and turning them into even more beautiful tables of numbers. So we do that by fitting models to them, and we get out things like stellar masses, star formation rates, metallicities, dust attenuation, and so on. I'm going to start out by just talking about the UV to the near infrared. Just a couple slides to orient you to this, and then we'll transition into talking about the mid and far infrared, which will be the focus of the talk. The reason to talk about this part of the SED first is because this is largely what powers everything redwards of it. And so the way we model the UV to the near infrared is by building these stellar models. Stellar models are composed of 2 different parts. One is stellar evolution models, so everything you learned in your stellar evolution classes in undergrad and graduate school, plus these spectral libraries. So you sort of paste these libraries onto the phases of the stellar evolution that they correspond to. Libraries are empirical, so spectra of real stars, or they're theoretical, where we couldn't get good spectra. This tends to be for types of stellar evolution that are either short-lived or very rare. So these models, in general, they're sort of Frankensteins of all these sort of different bits of theory and observations, and they're all pasted together. So there's a lot of uncertainties, but we won't really talk about them. But just so you know, there's a lot more uncertainties around shorter lasting phases like the TPAGB phase, or near subsolar abundances, because these are simply hard to find examples of in the local neighborhood. So if you're going to model an SED, the first building block is the star formation history. So here I'm showing 3 different types of star formation history here. They're essentially identical until 2 gig years have passed, where one has a burst of star formation, one continues to decline, and one quenches more sharply. And you can see the differences in the SED here. They should be pretty straightforward. Younger stellar populations emit more in the UV, older stellar populations emit less in the UV, and they have a stronger break here at 4,000 angstroms. We tend to model these things, in principle, this is star formation rate as a function of time. You could build an arbitrarily complex model for this, But when trying to extract information about this from the observations, people tend to fit simplified equations to this. So there's sort of a continuum here, going from more simple models, which you might imagine using when you have more simple data, or maybe when you're interested in a science question that doesn't depend so much on the age of the stars in the galaxy, and there are very few of those, unfortunately. Ranging to more complex models, which you might use if you have either better data, or if you want to marginalize over all the sort of uncertainties that come because you don't know the star formation history. And so this is sort of the base, and then we start building pieces on top of the star formation history. So the next piece here is sort of the stellar abundances, so the abundance pattern in the stars. This is one of the areas of modeling where the approaches we use are the most simple compared to how complex they could be. So you could imagine fitting models, and this is actually very common, where you just have a fixed metallicity. Here, just for reference, blue is lower metallicity, red is higher, and you can see those metal absorption lines in the UV crop up. But anyway, these models sort of range from a fixed metallicity, single metallicity for all stars, to a free metallicity, which is again applied to all stars. And then you can get very complex here, a distribution of metallicities for your galaxy, so stars have different metallicities and these are mixed. You can have some metallicity as a function of time. So older stars are generally more metal poor, younger stars are generally more metal rich. And then there's the full model, which is a completely free abundance pattern. And so this has some 70 plus components, because that's roughly how many elements we can model. So basically only Charlie Conroy fits these, and only to really, really good data. But yeah, so this is sort of the range here that you can imagine for metallicities. And then dust attenuation, this is sort of the other big pillar here. And here we have 3 SEDs ranging from dust-free to fairly dusty here. And again, we have varying levels of approximation. So very simple models might have fixed or no dust attenuation at all built into them. You can add this free attenuation component. Typically people build a dust screen, so the idea is there's stars, there's a screen of uniform dust, and then there's the observer. This is obviously a poor approximation, and we'll get into this later. You can imagine multi-component attenuation. So let's say there's a bunch of young stars, there's a screen of dust, there's all the rest of the stars, and then there's another screen of dust. That's sort of the next level up here. And then you start doing things like allowing the shape of the attenuation curve to vary. So when we say attenuation curve, we don't mean extinction curve. Extinction curve is only for one sideline at one time, so an extinction curve is caused by properties of the dust. Attenuation curve includes the effect of a mixed star-dust geometry, so it's sort of the full effect of having varying levels of optical depth to each star. And then, in principle, if you have enough data, you could also fit a sort of full radiative transfer model to a galaxy on the sky. This is rarely done. All right, so we take all these ingredients, we can model the UV to the near infrared.
Can I have a small question?
Yeah.
Shouldn't the dust be coupled to the metallicity in the previous stage?
Yes.
To some degree.
Absolutely. Yeah, physically there is every reason to believe that's true. In practice, it's almost never done because it's not quite clear how to do this in a good principled way. So yeah, that is a thing that people are only just starting now to put into their models. We know it should be true. The trick is we need a good set of theories to provide this mapping, to provide basically a good, reasonable prior for that. Okay, so we're going to transition now into the infrared. Oh, not yet. soon. Yeah, so the way we extend all this modeling into the infrared is by this simple principle called energy balance. And it sounds really simple and really obvious, but the next 15 slides or so are talking about ways in which it fails. So let's first talk about why it works and why it was a good idea and continues to be a good idea. The energy balance principle basically says you take all the energy attenuated in the UV and in the optical and in the near infrared and then stick it into the IR SED. This is super valuable for modeling purposes because it lets you fit this single physical model to the full SED. And assuming this gives you this really important handle on the obscured star formation rates. So this is a very powerful tool for modeling. It was first proposed by Elisabetta in 2007. At this point, I was a declared psychology major in undergrad, so it's been around for a while. And it's a critical part of building these models. And it's largely a successful part as well. For most galaxies, most of the time, energy balance works quite well. And there's a bunch of different ways to demonstrate this. So I'm just showing a couple here. One is this set of simulations by Chris Hayward, who was once here. Some of you may remember him. Here he's running some hydro simulations, full radiative transfer, and looking at galaxies from these different angles. So top down, along the disk, and so on, and running one of these SED modeling codes that assumes energy balance. And then here he's comparing the true attenuation due to dust compared to the recovered attenuation due to dust. And this is a pretty good proxy for how well the code is working in general, because this is one of the big outputs that we need to get in order to get the physics right. And he shows it works pretty well, in the sense that as you increase the dust in the simulation, you increase the dust that's recovered. There's obviously a tilt at higher values of dust, and we'll get back to that later. Another way to sort of show that energy balance works pretty well is by, again, taking this technique, applying it to real data. In this case, this is photometry of local galaxies. You fit it from the UV to the near infrared, or to the far infrared. You assume energy balance, and then you try to predict other things that are correlated with the star formation rate. In this case, H alpha. So here we're fitting a physical model to the photometry and trying to predict H alpha, and then we're comparing it to the spectrum, or to the real H alpha measured from the spectrum. And again, this shows that energy balance works pretty well in the sense that it agrees with other star formation rate indicators.